Hello everyone, welcome to Cafe Lapala Pula. Our project focus on a real business challenge faced by Cafe Lapala Pula, a Western-style cafe located near a university. Although the cafe offers many menu choice, 3 items stand out as the best seller, which is chicken tenders meatball, salad in ball and ramen chicken tenders. Each day, the cafe must decide how many portions of this best-selling set to prepare. This decision is not straightforward because the cafe must work within limited resource. Yum yum, looks so delicious.
They have limited working time, limited gross chicken supply, and at the same time, they must meet minimum customer demand for each menu.
If they produce too little, customers are unhappy.
What?
If they produce too much, ingredient and time are wasted. So, the main question is, how can the cafe choose the best number of each best-selling menu item to make the most profit every day without going over its limit?
Next, this is about model formulation for Lapala Pula Cafe. The following is table outlines about the preparation time, raw chicken usage, and minimum demand for each menu. Firstly, step 1, we have X1 represent numbers of chicken tenders meatball sets produced daily. X2 represent numbers of salad in bowl sets produced daily, and X3 represent numbers of ramen chicken tenders sets produced daily. Next, step 2, we have our objective function, which are to maximize total daily profit for Lapala Pula cafes. The objective function are represented by an equation max z equal to 3x1 plus 4x2 plus 2.5x3. The coefficient of each variable in the objective function represents the profit per unit of each menu. So, for step 3, we have our constraints. First constraint about preparation time. The cafe have 4 workers and each of them work 9 hours shift per day. 9 hours is 540 minutes, and with 4 workers, the total time work is 2160 minutes. So, for constraint 1, represent the total preparation time for the 3 menus used daily cannot exceed 2160 minutes. Constraint 2, represent the daily supply of raw chicken is limited to 50 kg. Constraint 3, represent the minimum production of chicken tenders meatball is at least 60 sets. So, for constraint 4, represent the minimum production of salad in bowl is at least 20 sets. The last constraint 5, represent the minimum production of ramen chicken tenders is at least 50 sets. Lastly, step 4, we have our optimization model, which are max z equal to 3x1 plus 4x2 plus 2.5x3, subject to 5 constraints stated in the previous slide, where x1, x2 and x3 must be greater than or equal to 0.
Next, I will explain the solver results for our linear programming project. Alright, to solve this problem manually, we use the dual phase simplex method, and this method is suitable because our model includes constraints that require artificial variables before reaching a feasible solution. So, after performing all the iteration, we obtain the final tableau, which is shown in this slide. From the final tableau, we can see that all the value in the 0 satisfy the optimality condition. Therefore, this solution is the optimal solution. Now, based on the final tableau, the optimal value of the objective function is 2z equals to 2,915 over 3, which is approximately Rm 971 ringgit and 67 cents. Now, after that, the optimal value of the decision variable are x1 equals to 60, x2 equals to 500 over 3, which is approximately 166.67, and x3 equals to 15. So, from this result, we can conclude that Cafe Lapala Pula should produce 60 sets of chicken tenders meatball, 166 sets of salad in bowl, and 50 sets of ramen chicken tenders per day. By following this production plan, the cafe can achieve a maximum profit of 971 ringgit and 67 cents per day. Next, we compare our manual calculation with the result obtained using Lindo. So now, what is Lindo? Lindo is a computer software specifically designed to solve linear programming and optimization problem efficiently. It is commonly used to verify results and handle complex calculation accurately. Now, if you can see, based on the Lindo output, we can see that the optimal solution obtained is x1 equals to 60, x2 equals to 166.67, and x3 equals to 50, with an objective value, function value of 971.6667. So, if we compare, these values are the same as our manual calculation using the dual phase method, with only a small difference due to rounding. Therefore, we can conclude that our model calculation is correct and the model we constructed is valid.
So next, we will continue on to the sensitivity analysis part. So I will explain the change in the right hand side. referring to the original model of Lapalapula, we changed 5 values of constraint. As we can see on table 3, the minimum demands for chicken tenders meatball 255, salad in bowl 215, 40 for ramen chicken tenders. We also changed preparation time to 2,400 and raw chicken required 260 kg. So originally, the optimal solution that we get is if Lapalapula should sell 60 sets of chicken tenders meatball, 166 of salad in bowl, and 50 sets of ramen chicken tenders per day to maximize profit of 971 ringgit 67 cents. So what we need to see is, will these changes in the right hand side of the constraint change the optimal solution?
Next, we know that it involves more than one changes on the right hand side of the constraint, so it is a simultaneous changes. Since it is not an individual changes, we do not need to take into consideration the feasibility ranges for the values. So from number 6 over here, it is from Lindo, the before and the after, which is from the original LP model to the new LP model after the changes. We can see the value of objective function changes as well as the value of x1, x2 and x3. So how do we get this? So number 7 here, we have 5 inequalities. This is the optimum conditions. If we substitute the values of D1 until D5 into each row, we can know whether it is feasible or not, and we can detect what is the value which is the new optimum values. For number 8 over here is when we substitute the values of D1 until D5 into the feasibility conditions. As we can see here, all the basic variables are feasible because it is non-negative. Since this happened, the current basis will not change, but the values for each basic variable will change. Hence, the new optimal solution will be x1 equals to 55, x2 equals to 255, x3 equals to 40. And some other variables also changes, and some will be 0. Thus, to conclude, Cafe Lapalapula need to sell 55 sets of chicken tenders meatball, 255 sets of salad in bowl, and 40 sets of ramen chicken tenders per day to get maximum profit of 1,285.
So we are going to discuss about the change in the objective function for sensitivity analysis. So referring to the Lapalapula Cafe original model, suppose that the profit was changed from 3 to 2, 4 to 6, and 2.5 to 0.5 of chicken tender with bowl, salad in bowl, and ramen chicken tender respectively. So we are going to find the new solution. So suppose that the objective function is changed from z equal to 3x1 plus 4x2 plus 2.5x3 to new z, which is z equal to 2x1 plus 6x2 plus 0.5x3. So then we are going to let D1 and D2 and D3 to represent the change in unit revenues for chicken tender meatball, salad in bowl, and ramen chicken tenders respectively. Then for the second step, we are going to subtracting the x from the new z with the original z, which is for D1, we are going to get 2 minus 3, which is negative 1, and then D2 is 2, and also D3 is negative 2. So because it has more than one change, then it is simultaneous change. So next, we are going to compare the alternative range that obtained from the Lindo. So as we can see from the Lindo, there's the allowable increase and also allowable decrease. So for our D1, which is within optimality range, so then the D1 is between the allowable decrease and also allowable increase, which is D1 is between negative infinity and also 3.67. For the D2 also are within the optimality range, which is between the 2.125 and also the infinity. And for the D3 also within the optimality range and between negative infinity to 2.833. So since all D1, D2 and D3 are within the alternative range, so which is the allowable increase and also allowable decrease, so therefore all conditions are satisfied and the optimality is unchanged. So for the new profit, we are going to substitute the value of T1, T2 and T3, and also we are going to substitute the value of S1, S2 and S3, which is we are going to get 3z equal to 3 plus D1 times S1 plus 4 plus D2 times S2 plus 2.5 plus D3 times S3, which is we are going to get the total of value, which is the 1,195.
Through this project, we learned that linear programming is not just a mathematical theory, but a powerful decision-making tool. We gain experience in translating a real-life business problem into a mathematical model. We also improve our understanding of optimization techniques, such as two-phase method. Most importantly, this project shows us how linear programming can help business operate more efficiently and increase profit. Overall, this project improve our problem-solving skills and help us appreciate real-world application of linear programming.